Welcome to this explainer. Today, we're going to dive into the absolute mind-blowing physics and, frankly, the engineering magic operating right now under the hood of Starlink's satellite network. We so often think of the internet as this invisible, weightless cloud that just magically surrounds us. But in reality, it's a very physical, very tangible infrastructure. And what we're going to look at today is how that physical infrastructure is moving off our planet entirely. We're going to see exactly how shooting beams of light through the absolute vacuum of space is completely rewriting the speed limit of global communication.
So let's start by challenging a pretty deeply held assumption about how we connect with each other globally. For decades now, we've all been told that underground and undersea glass cables, fiber optics, are the absolute pinnacle of internet speed. That's the gold standard, right? Well, it turns out that relying on those physical terrestrial cables actually imposes a major physical speed limit on our data. It's literally holding us back.
And here is the mind-bending reality of the situation. Routing data directly through the vacuum of space is actually 30% faster than our absolute best terrestrial fiber optic lines. 30%! That is a massive, massive leap in efficiency. I mean, if you're someone who relies on low ping and low latency, whether you're doing high-frequency financial trading, competitive gaming, or running secure global communications, a 30% reduction just completely changes the entire landscape of what's actually possible. But to really understand how we get that massive speed boost, we kind of have to look at how satellite internet used to work.
Okay, so think about the physical limitations of the older generation of satellites. They basically acted as simple relays. They'd catch a radio frequency signal from your house and then instantly bounce it right back down to a nearby ground gateway station that was physically plugged into the internet cables. The problem with that? Well, if that satellite is flying over the middle of the Pacific Ocean, or, say, a polar ice cap, there is no ground gateway to bounce the signal to. The satellite is effectively offline. But the new way? It completely severs that tether to the ground using a brilliant space daisy chain.
So the crucial upgrade that makes this all possible is called an OISL, or an Optical Inter-Satellite Link, or, to use the much cooler, much more popular term, space lasers. By equipping these satellites with these lasers, a ship out in the middle of the ocean can just send its data up to a satellite using standard radio frequencies. Then that satellite simply shoots a laser beam carrying your data to the next satellite and the next one, just hopping across the globe entirely in orbit until it finally finds a satellite that happens to be positioned over a ground station.
Now you might be wondering why on Earth, or I guess why in space, is a laser beam in orbit faster than a glass cable sitting on the ocean floor? It all comes down to friction. See, light traveling through physical glass cables on Earth is constantly bogged down by the glass's refractive index. The light is physically interacting with the material of the cable, which slows it down. But space is a pure vacuum. There's no atmosphere, there's no moisture, and there are absolutely no glass barriers to slow those light waves down.
And because it's traveling through that pure vacuum, the space lasers hit the absolute, unbroken speed of light limit. We are talking roughly 300 million meters per second. This is exactly how the network drastically reduces international ping and latency to those record-breaking lows we talked about earlier. You are, quite literally, communicating at the absolute fastest speed the universe mathematically allows. It's incredible.
Okay, let's pivot for a second to the extreme engineering precision required to actually pull this off. Because remember, these satellites aren't just politely hovering in one spot, they are absolutely screaming across the sky in low Earth orbit at roughly 27,000 kilometers per hour. That's about 17,000 miles per hour. They are moving unbelievably fast, and their positions relative to each other are just constantly shifting.
So, to maintain a stable data connection, the microtelescope on one satellite has to find and then perfectly lock onto another satellite that might be up to 1,000 kilometers away. Just try to wrap your head around that kind of distance for a second. That is literally like trying to spot a specific window in Paris while you're standing all the way over in Berlin. Now let's make it even crazier. Imagine this. You're standing on a platform that's moving at 17,000 miles per hour, your target is 1,000 kilometers away, and they are also moving at 17,000 miles per hour. And the target you need to perfectly hit with your laser is just a 100mm aperture lens. That's roughly the size of a standard dinner plate. It is just totally unbelievable engineering, because if your laser drifts off that plate for even a fraction of a second, the internet connection drops entirely. To pull off this insane high-speed ballet, each optical head is packed with an incredible suite of hardware. They use these highly advanced motorized mirror arrays and super-sensitive optical sensors that are just constantly tracking their target. They are performing real-time beam adjustments with sub-millimeter tracking accuracy, So it's this continuous, highly dynamic lock that absolutely refuses to let go, no matter how much the satellites drift or vibrate in the harsh environment of space. And because these lasers operate at incredibly high optical frequencies with very, very narrow beam spreads, they don't just hold a connection, they push a staggering amount of data. We are talking up to 200 gigabits per second on a single laser link. That's enough bandwidth to stream thousands of 4K movies simultaneously. And as a bonus, because the beam is so narrow and targeted, it requires way less power than a traditional widespread radio antenna, and it's naturally highly secure against interception or signal jamming.
So you might be thinking, how do they handle a massive 200 gigabit flow without the incoming and outgoing data just crashing into each other? Well, they use these space-hardened transceivers operating on the ITU DWDM optical C-band, which sounds like a mouthful, but in plain English, it means they separate the traffic by the literal color of the light. They have a red lane operating at 192.7 terahertz, strictly for transmitting data, and a blue lane at 193.5 terahertz, strictly for receiving. It's a perfectly synchronized, two-way highway made entirely of pure light.
But obviously, a single highway doesn't give you a global web. To get that, the satellites carry 3 to 4 of these optical heads each, which allows them to form 2 distinct types of connections. First, they hold permanent links with the satellites flying immediately ahead of them and behind them in their exact same orbital plane. Second, they execute temporary, highly dynamic links with satellites in adjacent or crossing orbital planes. And that fundamentally transforms the network into a massive, self-healing mesh wrapped right around the entire planet.
Let's actually trace how this action sequentializes for a single piece of data, say a simple text message sent from a cruise ship. First, the ship sends the data via standard radio frequency up to the nearest overhead satellite. Next, that satellite fires a 200 gigabit per second laser carrying your text right over to an adjacent node. Step 3 is where the real magic happens. As those satellites pass each other and eventually lose line of sight, they execute cross-plane handoffs in microseconds. They seamlessly pass your data stream to a brand new orbital node without dropping a single packet. And finally, a satellite positioned directly over a land-based internet backbone shoots the data back down to Earth. All of this happening in the literal blink of an eye.
Now, trying to route petabytes of daily data through this chaotic, fast-moving geometry is, frankly, a massive computational nightmare. To solve it, Starlink relies on graph optimization algorithms, which is actually really similar to what Uber uses when they batch-match riders to drivers. Using mathematical frameworks like the Hungarian algorithm, the software is autonomously calculating the absolute lowest latency path at all times. It is essentially predicting the future to know exactly where a satellite will be seconds from now, seamlessly adjusting that laser mesh on the fly.
And that leaves us with this final, truly mind-bending reality to ponder. We have spent well over a century laying physical cables across ocean floors and digging up streets just to connect our world. But what happens to the future of human connectivity, to international finance, and to our entire understanding of infrastructure when the absolute fastest way to communicate on Earth actually isn't on Earth at all? The vacuum of space has finally conquered the physical limitations of our planet, and the speed of light is officially off its leash. Thanks so much for joining me for this explainer. It's been a blast. Keep looking up.